In this video, what we're going to cover is we're going to cover slightly more complex integration, a step up from what we've done already. Now, we've covered when we've got a singular term, which is a power of x, and how we'd integrate that. So x to the n, integrating that to get x to the n plus 1 divided by n plus 1. What we're going to look at is when we've got a slightly more complex expression involving a linear style equation and powers that be with that. Now, think back to what we've done so far. If we remember, integral of x to the n dx equals x to the n plus 1 over n plus 1 plus c, our constant of integration. This is what we've covered so far. So this is the simple integration that we've covered up to this point. We're going to up the ante a little bit now and start to look at when we've got linear style functions. So ax plus b to the power of n dx. Now, when we're integrating one of these, it's very similar to when we took the derivative of it. Now, you'll remember that before, when we did differentiation, the derivative of ax plus b to the power of n was n, we brought the power down, ax plus b to the n minus 1, and then we multiplied it by a, our constant in front of x, because we essentially took the derivative of what was in the bracket. It's very similar with integration. The only real big difference is the power gets added on, plus we divide by our new powers. So the integral of ax plus b to the power of n equals ax plus b to the power of n plus 1. We add 1 onto the power. We then divide by this new power, n plus 1. But we have to take into account the fact that when we do the derivative, we get a factor coming out of here, our ax. So we get something coming out of here, so we have to divide by that as well. So it's ax plus b all to the power of n plus 1 over a times n plus 1 plus c, our constant of integration. And this can be expanded to if we've got a generalized function within that bracket. So if we had the integral of f of x, some function within the bracket to the power of n dx, we'd do f of x to the n plus 1. We'd still add 1 to the power. We'd then still divide by this new power, but we'd also divide by the derivative of the function to take into account the extra factor we'd have got when we took the derivative originally. We then add on c again at the end. Remember, this constant of integration has to go in every single time unless we've got limits like in our differential equation stuff. Now, the best way to explain these and show these is with an example. So, imagine I've got dy by dx equals 3x plus 1 squared, and I want to find y. We know that y is equal to the integral of dy by dx. We know that from previous work. So what we're going to have to do is integrate our dy by dx with respect to x. We know what dy by dx is, so we know that's going to be the integral of 3x plus 1 squared dx. Now this is our linear form. This is our ax plus b to the power of n. So when we integrate this and we find that, we have to follow the same steps. So our first step, raise the power by 1. So it's 3x plus 1 cubed. We then divide by this new power, so it's divided by 3, and we multiply that by the coefficient of our x. So we multiply that by, in this case, our 3. We then add on c, our constant of integration. So what that means, simplify this bit here, we get 1 over 9 times 3x plus 1 cubed plus c. So that would be our integral there. That would be our original function. Now, very quick and easy way to check this is take the derivative. So imagine I took this and I calculated dy by dx. Keep the constant in front, 1 over 9. Remember, to take the derivative of this, we bring the power here, reduce the power by 1, and then times it by the coefficient of x in here. So we bring the power down, we get 3, keep the bracket, 3x plus 1, squared, and then we times it by the coefficient in here, we times it by 3. Our plus c is just a constant, so that disappears when we take the derivative. So we end up getting 1 over 9 times 9, bracket 3x plus 1 squared. 1 over 9 times 9 cancels, and we get 3x plus 1 squared. That's what we started out with, so we've just confirmed it. This is a little check we can do if we want to make sure of it. So we've just confirmed that this technique works for simple linear functions. So simple linear functions are integral of ax plus b to the n dx. We know that that is, as we said, ax plus b n plus 1 over a times our n plus 1 with our constant of integration thrown in behind it. This form here works for any of these linear sorts of functions. However, if we change this from our linear function, so from our ax plus b, to another more complex one, we have to take that into account. And that was what our second formula allowed us to do. So let's imagine we say find f of x if f dash of x, our derivative, equals 2 bracket x squared plus 1 to the power of 3. Now this in here, it's no longer a linear function, it's a quadratic, it's x squared. So it's not going to be the simple integral of ax plus b to the power of n. This one here, we have to go back to our other one, which was the integral of f of x to the power of n dx. And we have to use that formula. So again, for this one, we keep our f of x, raise the power by 1, divide it by the new power, so our n plus 1, multiplied this time by the derivative of f. And then we add on our constant of integration, we plus c. This is the formula we have to use for this one because this is no longer linear, it's a much more complex function. So let's imagine that. So we know then that f of x is going to equal the integral of our f dash of x dx, it would be the integral of f dash x dx, which is going to equal the integral of 2 bracket x squared plus 1 cubed dx. Now, we then just integrate it as normal. The 2 in the front just stays as a coefficient, a constant. We then work our bracket. So we've got x squared plus 1. We raise the power by 1, so we get 4. We divide it by the new power times. Now this is where we have to look at this and calculate the derivative of what's in the bracket. If I have y equals x squared plus 1, my derivative of that, dy by dx, equals 2x. So bring the power down in front, reduce it there, and that's a constant. So instead of times it by some sort of coefficient on the bottom, it's 4 times the derivative, which is 2x. We then add on our c. Now we simplify this as we did before. So 4 times 2x on the bottom gives me 8x, but I've got a 2 on the top, so that cancels out, and I get x squared plus 1 to the power of 4 over 4x plus a constant c. So it's a slightly more complex integration because there's a slightly more complex function, but actually overall it's the same general-ish steps. There's just an extra step in terms of finding the derivative of whatever that f of x is within the formula. So we have to make sure we know these formula, and we have to make sure we know how to work them, how to apply them, and how to solve an equation that involves those two different styles of function.